Hey, Alex. So, I've been hearing a lot about quantum entanglement lately, and, Einstein called it spooky action at a distance. Like, what even is that really? Sounds like something out of a sci-fi movie.
Heidi, it totally does, right? But it's absolutely real, and it's pretty mind-blowing. Imagine two particles like photons or electrons whose states become linked. If you measure one, you instantly know the state of the other, regardless of distance. It's like they're communicating faster than light, which, well, it defies classical physics. Do you know what I mean?
Wow, so instantly, that's wild. And this isn't just like theoretical anymore, right? There's actual like really cutting-edge breakthroughs happening now?
Oh, absolutely. It's confirmed in experiments all the time. Just recently, in September 2025, scientists finally figured out how to identify the elusive W state of entanglement. That's a huge deal for quantum teleportation. And in January, Durham University even achieved long-lasting entanglement between molecules, which is crucial for quantum memories.
That's amazing for like quantum memories. So we're really getting better at creating and maintaining this entanglement. And I read something about AI being involved too. Like, is AI actually simplifying all this?
Yeah, totally. AI is actually playing a pretty big role now. In March 2025, for example, physicists with an AI tool called Pytheas discovered a much simpler method to untangle subatomic particles. It means you don't always need prior entanglement or those really complex measurements. This AI-driven approach could totally simplify developing quantum communication tech like the quantum internet, making it much more accessible.
The quantum internet? That sounds like super futuristic. But simpler methods, does that also mean we're getting smaller, more practical devices too?
Exactly. That's another huge step. Just this past January, a team developed this miniature, energy-efficient device that can create photon pairs maintaining quantum entanglement across any distance. This is like massive for making quantum tech portable and usable for computing, telecommunications, even high-precision sensors. It's truly exciting to see it go from huge labs to smaller setups.
Okay, so we're making it simpler and smaller, which is huge. But what's the big picture here? Like, what are the main applications of entanglement? Beyond just, knowing a particle state, what does it actually do for us?
Oh, this is where it gets really, really powerful, Heidi. Entanglement isn't just a curiosity, it's the absolute backbone for next-gen tech. First point, quantum computing. It lets qubits, these quantum bits, perform calculations in a highly coordinated way, potentially solving problems exponentially faster than classical computers. Researchers are actively creating and controlling entangled atoms in labs right now to build these incredibly powerful quantum systems.
Wow, exponentially faster? That's wild to even think about. So, like the next generation of supercomputers then. What about communication too? I mean, the quantum internet you mentioned earlier, how does entanglement fit there?
Right. Second big application, quantum communication and the quantum internet. Entanglement is the backbone of quantum key distribution, QKD, for ultra-secure communication. If anyone tries to eavesdrop on entangled particles, it instantly alters them, making detection inevitable. It's totally tamper-proof. Countries like China are already experimenting with long-distance transmission of entangled particles via satellites, which is pretty amazing.
Ultra secure communication and super fast computing. That's just mind blowing. So, what about other applications, Alex? Like, I've heard of quantum teleportation. Is that even real? And then, what are the biggest hurdles left?
Yeah, quantum teleportation is absolutely real. It's not like Star Trek, transporting people, but it is the instantaneous transfer of a particle's exact quantum state to another distant particle without physically moving the original. It's been experimentally realized, and those W-state breakthroughs are really pushing its potential. Plus, entanglement dramatically enhances precision in quantum sensors for much more accurate devices.
That's incredible. So much potential. But there must be significant challenges still, right? What's holding us back from, a full-blown quantum revolution?
Absolutely, Heidi. There are big hurdles. Maintaining entanglement over long distances without it falling apart, that's decoherence, is a major technical challenge. The tech for generating and detecting these particles is still developmental. We're aiming for fault-tolerant quantum computing systems that can detect and correct errors, which is a long-standing barrier for next-gen supercomputers. It's a huge frontier, but we're getting there.